Your calculus class isn't a waste of your time because here's a real world application where you can use what you've learned. You're going to want to subscribe like a ninja because if you see a problem like this on your AP exam, I want you to crush it. Let's get started. Say you've got this ice cream scooper and we want to find the critical points because we want to know how tall does this thing get because I want to put it in my kitchen drawer and I want to make sure it fits. So in this problem, let's just say that the ice cream scooper can be broken up into three parts that can be modeled by the following piecewise function. The handle on the very left can be modeled by the line y equals 1/2 x. And then the scooper dome part can be modeled by this quadratic function, negative x minus 3 all squared plus 2. And then finally, the little lip at the very right end can be modeled by the constant function y equals 1. So the reason why the critical points are important here is because we want to know both globally at all ends of the piecewise function interval and locally the critical points, and we want to take the maximum value to see how tall does this thing get. Okay, so the way I want to approach this on an AP exam, right, is I would first want to take one of the functions in the piecewise function. Now, I'm going to start on the very left. So starting with y equals 1/2 x, we want to find the critical points, and there are two kinds, the local and the global. So for the local, what you do is you take the derivative function, and when you take the derivative of 1/2 x, you will simply get 1/2. And to find the local critical points, what you want to start with is setting the derivative function equal to 0. And the reason why we do this is that when the rate of change, or in other words, the derivative function is 0, oftentimes that'll mean that a function is changing its behavior. Now, in the case of a line here, the derivative function is actually always this constant 1/2, and it'll never be 0. And we expect that, right? Because for a line, the derivative function simply is the slope value. So we know that there are no local critical points for this, but we still need to make sure we don't skip the step of finding the global critical points. And the way you do that is you take the interval that this is defined over, 0 to 2, and for each end of the interval, you plug in that value for x. And so f of 0, the left end of the interval, will give you 1/2 times 0, resulting in 0. And then for the right-hand side of the interval, when you plug in x equals 2, you will get a value of 1. So there are no local critical points, but you have these two global points to look at, 0 and 1. And so we'll take the maximum. In this case, the line has a maximum value of 1 over the interval. Now, we're going to repeat this for the middle dome part. And I want to go back up to the picture because here's an important thing to recognize. Because we're modeling that dome as a parabolic function that's concave down, remember that a quadratic function has a property of having a vertex. Now, in the case of a concave down function like this one, we know at the vertex that the function has the maximum value there. Because of the concavity, we know that to the left of the vertex, the function is increasing when approaching the vertex from the left, and then after the vertex, it's basically dropping off. And the other thing you have to remember is that at the vertex itself, the behavior of the function is changing from increasing to decreasing. So this means that we expect the derivative function to actually equal 0. So in other words, taking the critical point at the vertex, we expect that the slope at that point is 0. And so when you want to actually find that local maximum at the vertex, it's the same idea. We're going to go ahead and we're going to take that second piecewise function, which is that quadratic function, find its derivative and set it to 0. And so given negative x minus 3 all squared plus 2, using the chain rule, we will end up with a derivative function that's going to be the negative in front, which is -1, times the old power you've raised the stuff in parentheses to, which is 2. We're going to bring it in front. And then times what you have in parentheses, the x minus 3, all raised to 1 power. That's 1 less than what it used to be, so 1. And then times the derivative of the inner function to complete the chain rule. Now, the derivative of the inner function, x minus 3, is simply 1. And of course, the plus 2 at the end drops off because the derivative of that constant will be 0. Okay, so simplifying the derivative function of the quadratic function, you're going to get negative 2x plus 6 after you distribute the negative 2 through. By setting this to 0, this is where we find that local maximum. When 0 equals negative 2x plus 6, you're going to solve for x. And so after you get 2x equals 6, you'll find that x simply is 3. Now, here's an important critical step to not miss, pun intended. You want to make sure that you put that value of 3 back into the original function. We're not looking for finding the rate of change at 3. We already know it's 0. We're looking for what the actual function rises up to at x equals 3 at that local maximum. So when you evaluate f of 3 and you plug it in for x, you're going to get 3 minus 3 squared all times -1. That all cancels out, plus 2. And you'll have a result that's simply going to be 2. Now, don't forget, you have to still find the global maximum and minimum values. We only found the local before with the derivative function. So going back to the original function, looking at the interval, this is all defined over 2 to 4 for x. We got to plug in each endpoint back into that function. So f of 2 will be negative, in parentheses, 2 minus 3 all squared plus 2, giving you a result of 1, which also happens to be the same result you'll get when you plug in 4 for x. Okay, so for this parabolic function now, we've got this set of local and global critical points, 2, 1, and 1. We want to find the maximum because we care about how high this ice cream scooper gets. The maximum here is 2, so we're going to save that off as well. The last function to the very right, that constant function y equals 1, is very simple, right? We already know that it's basically a horizontal line, and so there's no rate of change. The derivative function is 0, and the maximum is just simply wherever you are on that line. It's the same value, right? It's 1. So bringing everything together, from the first piecewise function, 1/2 x, we knew the max was 1. For the parabolic function, we know it's 2 as the maximum. And for this last function, y equals 1, the max is 1. When you compare all the values together here, you get a final answer of 2.